Hello, today we are continuing in our A-level physics revision series, this time looking at thermodynamics and thermal physics. If you take an ideal gas, and we'll consider what one of those is in a moment, and for a given temperature, a constant temperature, you plot the pressure of that gas against the volume, you will get a curve like that, which satisfies the equation that the pressure times the volume is a constant, which for the moment we'll simply call C. If we were to plot pressure against 1 divided by the volume, then we would get a straight line, which suggests that pressure is proportional to 1 over volume. Remember that this is at constant temperature. That's called Boyle's law. Now there's another law called Charles' law. And Charles' law relates volume to temperature. And if you plot volume against temperature, you get a straight line, which means that volume is directly proportional to temperature. But if we extend the axis this way and then plot backwards, we find that this line crosses at this point here, which is approximately minus 273 degrees Celsius. And at that point you can see that the volume of the gas is now 0. And it clearly can't go any further. It cannot become a negative volume. So that's as far down as it can go, and we call that point absolute zero. And that is 0 in the Kelvin scale. So 0 degrees Kelvin equals minus 273 degrees Celsius. But every degree Kelvin is equal to 1 degree centigrade. In other words, the divisions on the scale are the same, but 0 Kelvin is minus 273 degrees Celsius. You might just notice a convention here. When we're talking about degrees Kelvin, we don't put the little degree signal in here. Whereas when we're talking about degrees Celsius, we do put that little degree symbol in there. Now finally we have a pressure law, and the pressure law relates pressure to temperature. And once again it's a straight line. And once again, if you project it backwards, you find that the pressure becomes 0 at minus 273 degrees Celsius, which is 0 degrees Kelvin. And that tells us that pressure is proportional to temperature. So we have that pressure is proportional to 1 over volume, volume is proportional to temperature, and pressure is proportional to temperature. And if we put all of those together and combine them, we get that pressure times volume over temperature is a constant, which I'll call C for the time being. But that constant is obviously going to depend on how much gas you actually have. So let's consider 1 mole of a gas. Now, a mole is simply the atomic weight of the gas expressed in grams. So for example, hydrogen, the atomic weight is 1, so 1 mole of hydrogen is 1 gram of gas. Then we would say that PV over T equals R for 1 mole of gas. And R is the molar gas constant, and its value is 8.31 joules per mole per degree Kelvin. If you have n moles of the gas, then PV over T will equal n, which is the number of moles, times R, which is the molar gas constant. And if you rearrange that formula, you get that PV equals nRT. And that, as I've said before, applies to an ideal gas. So what is an ideal gas? Well, it has several qualities. First, there must be a large number of particles, or molecules in the gas. Second, they must be moving rapidly and randomly. Third, their motion follows Newton's laws of motion. Fourth, all the collisions between the molecules are perfectly elastic, no energy is lost. Fifth, there's no attractive forces between the particles. Sixth, all the forces apply instantaneously. And seventh, the particles have negligible volume compared with the volume of the gas. That's quite a hefty set of constraints, but in practice, most gases behave like an ideal gas if two things happen. One, the pressure is not too high, and two, the temperature is much higher than the boiling point of the gas. Temperature scales tend to have fixed points, such as the centigrade or Celsius scale has 0 degrees for the freezing point of water and 100 degrees for the boiling point. But these are actually temperature dependent. Is there a way to come up with a fixed value that doesn't depend on pressure? And the answer is that there is. And the Kelvin scale has two fixed points. 0 degrees Kelvin is the point we established before. It's when volume or pressure is reduced to 0. The second fixed point is what's called the triple point of water, which is 273.16 degrees Kelvin. It is the one and only place where ice, water and steam all sit together harmoniously. They are in equilibrium. Now clearly that doesn't happen at room atmospheric pressure because ice and water are at 0 degrees and water and steam are at 100 degrees. But if you reduce the pressure sufficiently, there comes a point where ice, water and steam all coexist, and that's called the triple point of water, and it's 273.16 degrees Kelvin. Now the speed of a particle, or the velocity of a particle, which of course is also determines the energy, because the energy is half mv squared, that's the kinetic energy of a particle, is proportional to the temperature. The higher the temperature, the higher the velocity. That doesn't mean, of course, that all the molecules in a gas are travelling at exactly the same velocity. If you were to plot the number of particles in the gas compared with their velocity, then for one temperature, let's say this is 200 degrees Kelvin, you would find that there would be a distribution of velocities. But this would be the average velocity for 200 degrees Kelvin. If the temperature goes up to, say, 500 degrees Kelvin, then you would find that the distribution spreads out like this and the average has gone up. You will notice that as the average temperature increases, so the average speed increases, the maximum particle speed increases, and the distribution curve spreads out. This is more spread out at 500 degrees than this is at 200 degrees. We must remember that particles or molecules in the gas are colliding all the time, and therefore they're transferring energy from one to another. But the total energy of all the particles will remain the same for a given temperature. Now let's consider a box of side, it's a cube of side L. And it has N, capital N, molecules, not moles, but molecules of a gas inside it. What is the pressure on, let's say, this face of the cube? Well, pressure, we know, is force divided by area. And force is the rate of change of momentum. P is momentum. Well, momentum is mass times velocity. So we can say that that is dmv by dt. And since the mass doesn't change, that is m dv by dt. And dv by dt, of course, is simply the acceleration. So force is mass times acceleration, which is Newton's second law. Now let's make an assumption which is not as daft as it sounds, that the molecules in the box are moving in only three directions. A third of them are going left to right, a third of them are going up and down, and a third of them are going back and forth. And although you will say that the molecules will be travelling in all directions, and that is perfectly true, the fact is that you can always resolve a velocity into one of these three directions. They are the coordinates of a velocity. You can resolve them into those coordinates. And let's further assume that all of those molecules are travelling at an average speed v. In fact, to be technically true, what we should say is that it is the root mean squared speed. To get the root mean square speed, you take all the speeds, and you square them, and then you add them all together, so that's the sum of the squares, and then you take the square root, and that is the root mean square. But I shall use the general term average speed or average velocity. Now let's consider one molecule which is travelling from left to right, and it hits this wall, and as it does so, it is travelling in this direction at v with mass m, so it has momentum mv, and when it hits the wall it bounces back, still with the same mass but now with velocity in the other direction. What is the change in momentum? The change in momentum dp is 2 mv, because it was going in mv in this direction, now it's doing mv in that direction, the total change is 2 mv. How often will that molecule hit that wall? Well, it hits the wall, it rebounds, it then travels all the way over to this wall, it rebounds again and it comes back. And when it does that, it has travelled a distance of 2L, there and back. So its distance is 2L. But it's travelling at speed v, and therefore the time to travel there and back, the distance 2L, is 2L divided by v. And now we can write down that dp by dt, which is the rate of change of momentum, is dp, which is 2mv, divided by dt, which is 2L over v. And that comes up there and becomes v squared. And that equals mv squared divided by L per molecule. So the force, which is dp by dt, is equal to mv squared divided by L per molecule. But what we said was that there were a total of n molecules in the box, and a third of them were travelling from left to right. And that means that the total force exerted by all the molecules on this surface is going to be equal to the n divided by 3, which is the total number of molecules, times the force of any given molecule. And that is the force on this surface. But pressure is force over area. And the force we know is n over 3 mv squared over L, divided by the area. Well, what's the area? The area of this wall is L times L, L squared. And that gives you nmv squared divided by 3L cubed. But what is L cubed? L cubed is simply the volume of this box. So we can replace L cubed by volume. And that means that P equals nmv squared divided by 3V, capital V now, where V stands for volume. And rearranging that, we can say that PV, by taking the V up here, is equal to nmv squared divided by 3. But we've already shown that PV is nRT, where n is the number of moles, R is the molar gas constant and T is the temperature. And if we rearrange this equation here, we get that a half mv squared, which of course is the energy, equals 3 over 2 n over n RT, where n is the number of moles, n is the number of molecules, and R is the molar gas constant. Now, it was Avogadro who said that 1 mole of gas has the same number of particles. It doesn't really matter what gas it is. If you take 1 mole of it, you will have the same number of particles. And that's Avogadro's number. And that is 6.02 times 10 to the 23 particles per mole. And that's often given Na. So now we can write that the total number of molecules in the box is equal to the total number of moles times the Avogadro number Na. And that means that n divided by n, this term here, is equal to 1 divided by the Avogadro number Na. So now we can write that the energy, which is half mv squared here, equals 3 over 2. N over n is now 1 over Na, RT. And since R is a constant and Na is a constant, we can define R over Na as a new constant which we shall call K. And K is called the Boltzmann constant, and its value is 1.38 times 10 to the minus 23 joules per Kelvin. And what we can say is that R is the gas constant for 1 mole of gas, whereas K is the gas constant for 1 particle or 1 molecule of gas. We're now going to look at thermodynamics. There are 4 laws of thermodynamics which can be expressed in varying ways. I'm going to keep them simple today. The 4 laws are 0, 1, 2, 3. The reason there is a 0th law is that the first 3 were already formulated when someone realised that there was a necessary law before those 3, which had to be called the 0th law. The reason was that the 3 laws of thermodynamics referred to temperature, and then somebody realised that no one had defined temperature. So consequently, the first law, which is called the 0th law, defines temperature. The first law says that heat is work and work is heat. The second law says that heat cannot of itself flow from one body to a hotter body. You can't get heat to move to a hotter body. It doesn't flow upstairs. And the third law essentially says that you can never get to absolute zero. You can never get to 0 degrees Kelvin. The first law, which defines temperature, is often described in this way. Let us take a body, which we'll call body A, and that is at a certain temperature. And now we'll take another body B, which is at another temperature. And what we say is that if we bring these into thermal contact, such that heat can flow, heat will always flow from the hotter body to the cooler body, never the other way round. And it will continue to do that until those 2 bodies are what are called in thermal equilibrium, which is kind of another way of saying they're at the same temperature. And what the first law says, the 0th law says, is that if 2 bodies are in thermal equilibrium, that is, heat no longer flows between A and B, and if there's another body C which is also in thermal equilibrium with A, that is to say A and C are at the same temperature and A and B are at the same temperature, then it must follow that B and C are at the same temperature and hence in thermal equilibrium. There was a very well-known song in the 1960s by a popular singing duo called Flanders and Swan. They wrote songs about the most unlikeliest of subjects, and one of them was about thermodynamics. And their great song was that heat is work and work is heat. Heat is work and work is heat. Heat cannot of itself flow from one body to a hotter body. And those are simply just the two expressions of the first and second laws of thermodynamics. Let's look at the first law. According to Flanders and Swan, but actually to physicists before that, the total amount of energy, or rather we talk about energy change since you can never be sure precisely how much energy you've got, so we call that delta U, which is the energy change in a gas, is equal to the total amount of heat put in plus the total amount of work done. We always use positive terms when we're putting heat or work into a system, and we use negative terms if we're getting heat or work out of a system. So just to recap, delta U is the change in total energy of a system. Delta Q is the change in the heat going into the system, and delta W is the change in work being done to the system. What does this mean? Well, let's take a container into which we will put a piston or a plunger. That's free to move up and down, but nothing can escape outside the plunger, and we're going to have a gas inside that plunger. Now we might press down on the plunger and squash the gas. What we're doing is we are doing work, and consequently there's no heat going in, but the energy of that gas will increase because we're putting work in. Alternatively, we could take exactly the same arrangement. Here's the plunger, here's the gas, but instead of pushing it down or pulling it up, we put a flame underneath to heat it up. We're now putting heat in, delta Q. We're not doing any work, but heat in. If that plunger doesn't move, then what will happen is that the gas will heat up and its energy will increase. So delta U will equal delta Q, the heat in. Now there are different ways in which all this can happen, different ways in which energy can change. There's a process called adiabatic, which means that there is no heat in and no heat out, but the temperature inside the system can still change. The way this usually works is that you take a system here and you surround it by some kind of insulating material such that no heat can get in and no heat can get out, and that's called adiabatic. The second type of change is what's called isothermal. The temperature remains constant, and the way this is done is that the system, here's the system, whatever it may be, is placed in what's called a heat bath. This is usually a fluid of constant temperature that you maintain at constant temperature, and it's got so much heat in that heat bath that it can ensure that the temperature of this system remains absolutely constant, and that's called isothermal. And the third type of change is what's called constant volume, or in some cases constant pressure, where you make the changes but you ensure either that the volume doesn't change, that is to say that stays the same volume, or the pressure acting on that system doesn't change. Let's just consider an example of three changes. We're going to plot pressure against volume. And what we're going to do in these three examples is we're going to take a gas that has a volume V1 and we're going to take it down to a lower volume V2. And we're going to start with the pressure at that point and the volume V1. So our starting point is a pressure with a volume V1. Now there are three ways that we can get down to volume V1. That's where we've got to get to. The first is the adiabatic, and that will look like a curve like that. The second is isothermal, and that will look like a curve like that. And the third is constant pressure, and if constant pressure means that pressure doesn't change, so it will simply go like that. Now, what does that actually mean? How can we achieve this? If we're going to reduce the volume but not change the pressure, the only way we can do that is to reduce the temperature. So for path 3, the temperature goes down. For path 2, isothermal, that's a constant temperature. T is constant. For that's path 2. Path 1 is the adiabatic change, and in that case the temperature is going to go up. So essentially you achieve these 3 different paths depending on what happens to the temperature. In this case the temperature must go down. You actually physically have to reduce the temperature in order to get the volume to decrease. Here this is just a straight volume change with a consequent pressure increase, but all at constant temperature. And here you've got a volume decrease, a pressure increase, but also a temperature increase, and that's adiabatic. We can now consider what's called a heat engine, and it's sometimes also called a Carnot cycle. Once again, we're going to plot pressure against volume. And we're going to go through 4 points, each of which, as you will see, has a distinctive pressure and volume, pressure and volume, pressure and volume, pressure and volume. And the path we're going to take goes something like that. This path is isothermal, which means that there is no temperature change. This path is adiabatic, which means that there is no heat in, no heat out. This path is isothermal again, constant temperature, and this path is adiabatic, which means no heat in, no heat out. So you can, by the same process that we achieved these changes, you can achieve these changes. Isothermal, constant temperature, adiabatic, no heat in, no heat out. And you can go right the way round until you come back to where you've started. And the area within this curve is equal to the work done. And that's either by the system, you might get work out, or to the system, you might have to put work in. Now let's go back and look at this term that we derived earlier. PV equals nKT, where n is the total number of molecules, K is the Boltzmann constant, and T is the temperature. This term PV is in fact an energy term. We can demonstrate that fairly easily. What is pressure? Pressure is force over area. But what is area? Well, area is just a distance squared. What is volume? Well, volume is a distance cubed. And so pressure times volume is force times distance. But what is force times distance? That equals work or energy. So PV is an energy term. And what we can derive from this is that PV, which is energy, equals KT for a single molecule, because it's nKT for n molecules, so it's KT for a single molecule. And this now relates the energy of the gas to its temperature. It shows why, as the temperature increases, the energy increases. And it also means that we don't really need a temperature scale. We could, in fact, describe all temperatures in terms of energy simply by multiplying the temperature, which of course has to be in degrees Kelvin, by the Boltzmann constant. That does not, of course, mean that every single molecule in a gas will have an energy equal to KT. If you look at the number of molecules in a gas and you look at their energy, then you're probably going to find that there will be a distribution. Some molecules will have a much higher energy, some will have a much lower energy because they're constantly colliding with one another and transferring energy, but the average is going to be KT. Now let's think about particles in matter. They are held together by some kind of bonds. We don't need to work out exactly what kind of bonds at this stage, simply to say that particles that are in a solid are obviously very tightly held together, particles that are in a liquid are much more loosely held together, and particles that are in a gas are barely held together at all. So in other words, the bonds are much tougher and tighter in a solid than they are in a liquid, and they're tighter in a liquid than they are in a gas. So what do you need to do if you want to change the state of a solid to a liquid? Let's say you want to take ice and you want to melt it. The ice will have very tough bonds between the particles, the molecules, and they need to be broken. And how do you break bonds? You have to put in energy. And we've just shown that the energy equals kT. So you might think that you can break these bonds by having an energy which equals kT, and that energy will be the energy that's capable of breaking the bonds. Let's say that the energy needed to break a bond is epsilon. Then what we would be saying is epsilon equals kT, the bonds get broken. But actually that's not quite true for the reason that I just showed in the graph, that if you plot the number of molecules against their energy, you get a distribution. And the average distribution, I said, was kT. But way up here somewhere, right towards the far end, there might be molecules that have the energy epsilon. So the average doesn't necessarily have to be epsilon. If some of the molecules have an energy epsilon, then they will have the capacity of breaking those bonds. So in fact, the bonds can start to be broken when the average energy is very much lower than epsilon, as long as there are some fast-moving molecules that have sufficient energy to break the bonds. And what typically happens is that if epsilon is equal to about 15 times kT, or if epsilon divided by kT is equal to 15, then the process of bond breaking will begin. And that enables us to talk about what's called the Boltzmann factor, which is the exponential of minus epsilon over kT. And what we said was that if epsilon over kT is 15, then the process will begin to start, which means that if e to the minus 15, because epsilon over kT is 15, equals approximately 10 to the minus 7. And what that means is that if 1 in 10 to the 7 particles has enough energy to overcome the what's called activation energy, or the bond energy, to break the bonds, then that process will begin. There are, of course, millions of particles, millions of molecules, and consequently, if just some of them have enough energy, then those bonds can be broken. And the rate of the reaction is given by this formula here. Finally, I want to look at the subject of specific heat. Specific heat is energy, and it's the energy required to make the temperature increase or indeed decrease. You put energy in to get the temperature to go up, you take energy out to get the temperature to go down. And specifically, the specific heat is the energy or the heat needed to raise the temperature by 1 degree Celsius or Kelvin, it's the same, per kilogram of the material. So if you've got 1 kilogram and you want to raise the material's temperature by 1 degree, then you have to put in that amount of energy, and that's the specific heat. So essentially, the specific heat or energy is equal to the mass in kilograms times the specific heat times the change in temperature that you want to achieve. The specific heat of water, for example, is 4180 joules per kilogram per degree Kelvin. So if you want to raise 1 kilogram of water by 10 degrees, you need to put in 10 times this amount. In other words, the total energy or the total heat that you need to put in is the mass, which is 1 kilogram, times the specific heat, which is 4180, times the temperature change, which is 10. So you'd need to put in 41,800 joules of energy or heat in order to raise 1 kilogram of water through 10 degrees. Now that's the specific heat needed to take a product and increase its temperature without changing its state. Suppose you have ice and you want to convert it into water, then that's called the specific heat of fusion. And to take 1 kilogram of ice and to convert it into 1 kilogram of water, both at the same temperature, both at 0 degrees Celsius, you need 80 times that specific heat. You need 80 times to get 1 kilogram of ice changed to water. No temperature increase at all. It's just that's the amount of energy to break the bonds to turn ice into water. And to turn water into steam, you need approximately 500 times this amount. Now remember, this is the energy you need to take 1 kilogram through 1 degree Celsius or 1 degree Kelvin. If you took water from 0 degrees to 100 degrees Celsius, that is from freezing point to boiling point, but without it changing state, in other words, it remains water all the time, you'd need to use 100 times this amount of energy. Once you got it to 100 degrees centigrade, if you want the water to boil, you have to put in 500 times this amount of energy, which means you're putting in 5 times as much energy just to get the water to change from water to steam as you had to put in to get the water to go from freezing point to boiling point.